So at GCSE, we spent a lot of time drawing electron shell diagrams. I'm just going to draw one quickly here for sodium. So sodium has the atomic number 11, which means it's got 11 electrons in total. And if I were to draw an electron shell diagram, I would put 2 electrons in the first shell. I would then move to the second shell and I would draw in 8 electrons. And I would then move to the third shell to put in the remaining electron. And I've got 2 and 8 is 10 and 1 is 11. I've drawn all 11 electrons. So when I'm drawing my electron shell diagram, I always start with the first shell. That's the shell here on the inside, the shell closest to the nucleus. The reason I start with the first shell is because it is the shell lowest in energy. The first shell can only hold 2 electrons. So when it is full, I have to move to the second shell. I do not move to the second shell until the first shell is full. The second shell can hold a total of 8 electrons, so when the second shell is full, I then move to the third shell. Again, as you go from the first to the second to the third, the shells are increasing in energy, so they're getting further from the nucleus and they are increasing in energy. At A level, we're going to move away from this electron shell model and instead look at orbitals. But the principle is exactly the same. An orbital is just the region around the nucleus where you find a pair of electrons. If we look at our electron shell diagram, again, it was just the region or the space around the nucleus where you found your electrons. When you're drawing these electron shell diagrams, you would never put an electron here in the space between the two shells. That's because electrons were restricted to the shells themselves. Similarly with orbitals, they are the region around the nucleus where you find electrons. You can't just find electrons anywhere. They are confined to the orbitals. So if we look at the orbital model, it's quite it's comparable to the GCSE model. So at GCSE, we saw that the first shell could hold 2 electrons. At A level, instead of calling it the first shell, I'm now going to be referring to it as the 1s orbital. Okay, so an orbital, each orbital can hold a pair of electrons. If I've got 1 orbital, then I can hold 2 electrons, exactly what we had at GCSE. The second shell at GCSE we saw could hold 8 electrons. If I need to get 8 electrons into that second shell, then I'm going to need 4 orbitals, as each orbital can only hold 2 electrons. And that's exactly what I've got. So my second shell at GCSE, at A level, I've now got a 2s orbital and 3 2p orbitals. Each orbital holds a pair of electron, giving me a total of 2, 4, 6, 8 electrons, exactly what we had at GCSE. At GCSE, it appeared that the third shell was full with 8 electrons. This is not in fact true. The third shell can hold 18 electrons. If it can hold 18 electrons, but each orbital can only hold 2, you are going to need 9 orbitals in total. Like with the first and second shell, you are going to have an s orbital. You will also have p orbitals, but you will need a new set of orbitals called the d orbitals in order to take those extra electrons. So we said you can hold 18 electrons, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. Each orbital holds 2, 18 orbitals in total, 9 orbitals in total, making up that third shell. The fourth shell is not something we really encountered that much at GCSE, but you need to know at A level that it can hold 32 electrons. If it can hold 32 electrons, then you need to have 16 orbitals, as each orbital can only hold 2. So like the shells above, you've got an S, you've got 3 Ps, you've got 5 Ds, and you now have 7 F orbitals, again, each which holds 2. So first shell here, we can see we have got 2 electrons in total, only 1 orbital needed. Second shell, because we need to have 8 electrons in there, I need 4 orbitals. Third shell, I need 18 electrons, meaning I've got 9 orbitals. Fourth shell, 32 electrons, means I need 16 orbitals. Now this may seem, potentially difficult to learn off, but there are certain patterns, okay? As you go from the first to the second to the third to the fourth shell, you are always gaining a new type of subshell and a new type of orbital. So the first shell only has the s orbitals, the second has s and p, third has s, p and d, fourth s, p, d and f. So the shell number matches the number of different subshells that you have. The other pattern you can see is that each time you gain a new subshell, that subshell has 2 additional orbitals to the subshell that came before. So if we look here at the p orbitals, you've got 3 p orbitals. When you gained a new subshell, the d's, you had 5 d orbitals, so 2 more than what you had when you had just p. When you gained the 4f subshell, you gained another 2 orbitals, so I've got 7 of the f's compared to 5 of the d's, compared to 3 of the p's, compared to 1 of the s's. So each time you're gaining this new subshell, this new type of orbital, that subshell is bigger by 2. So I've only got 1 s, I've got 3 p's, I've got 5 d's, I've got 7 f's. The other thing that is really important, not only is knowing the different orbitals that make up the shell, but you need to know their relative energies. For the most part, this is pretty straightforward. So if I reveal this diagram here below, I've drawn it out with energy on the y-axis, and as you move up the y-axis, the energy is increasing. So I'm just going to cover this here for a second, okay? So starting off here, the 1s, which represents the first shell, is the lowest in energy, the shell closest to the nucleus. Then you move into the second shell, and you will see that even though the 2s and the 2p orbitals are all part of the second shell, that they are not the same in energy. The 2s is slightly lower than the 3 2p orbitals. The 3 2p orbitals are exactly the same, but the 2s is slightly lower in energy than the 2p. Now this is not something we accounted at GCSE. At GCSE, when we looked at the second shell, all of the electrons in the second shell were equivalent in energy. At A level, that's not the case. The electrons that occupy the 2s orbital are slightly lower in energy than the electrons that will occupy the 2p, even though they are all part of the second shell. If we move on to the third shell, again, we've got the 3s lower than the 3p, and the 3p being lower than the 3d. So far I've got first shell, then I've got the second shell higher in energy, then I've got the third shell higher in energy. That's consistent with what we had at GCSE. You just need to note that within that shell, S is lower than P and P is lower than D. The fourth shell, so I've got my 4S, my 4P, 4D and 4F. When I introduce the fourth shell, you will actually see that the 4s, even though it's part of the fourth shell, is slightly lower in energy than the 3d, which is part of the third shell. The 4p, as always, is higher in energy than the s, and it is higher in energy than the 3d. At A level, you're not required to use the 4d orbitals or use the 4f orbitals, so we don't need to include it here, which means that this diagram I've drawn here is complete. This is all of the information you need for A level. So they're increasing in energy. What you need to look out for is that 4s is actually lower than 3d, and then you've got 4p at the top. Now the reason this is important to know the relative energies is just like at GCSE, you always fill the lowest energy level first, and you don't move on to the next energy level until that level is full. So if we let's look at, say for an example, calcium, which is one that we would have looked at GCSE, and you have got 20 electrons in total for calcium to fill in. If I just quickly draw what we would have done at GCSE, we would have put 2 electrons in the first shell, 8 in the second shell, 8 in the third shell, and then put the remaining 2 in the fourth shell. So at A level, we're going to do something similar. We're going to start with the lowest energy level. Remember, each orbital can hold 2 electrons. So I'm going to put 1 electron in the 1s, and then I'm going to put the second electron into the 1s. And underneath, I'm going to write it as 1s2, because that's how many electrons I've got in that s orbital. I don't move on to the 2s until the 1s is full. I put an electron into 2s and then another electron into 2s. My 2s orbital is now totally full. Then I move on to 2p. Remember, 2s is slightly lower than 2p, so I don't move into 2p until 2s is full, even though they're both part of the second shell. When I'm filling my 2p, all my 2p orbitals are exactly the same in energy. So the electrons will actually fill those orbitals singly first. And the reason they do that is electrons are negatively charged. So if they have the option of having an orbital to themselves, they will take it, as long as it doesn't mean moving to a higher energy level. Because your 3 2p's are all exactly the same in terms of energy, they will fill them singly before going back and filling them in pairs. So now I've got my 2p6. So far I've assigned 2, 4, 10 electrons. I've got 20. So then I move into my 3s and I fill up my 3s before moving on to my 3p. And once again with my 3p, I fill singly 1, 2, 3 before going back to fill in pairs 4, 5, 6. And that leaves me with my 3p6 totally full. So now I've assigned 2, 4, 10, 12, 18 electrons. I've only got 2 more electrons to go. You might be inclined to move on to the 3d to fill in those remaining 2 electrons, but it's always the lowest energy levels that fill first. 4s, although part of the 4th shell, is lower in energy than the 3d, so I'm going to put my remaining 2 electrons into the 4s. That means I've got 0 electrons in 3d, and I've got 2 electrons in my 4s, and that's my electron configuration for calcium using my A-level model. You don't need to include the 3d0, it would be fine to leave it out and just write 4s2. Now when you're asked to do this in the exam, you are not required to draw out this whole big diagram, you're just required to write the electron configuration as I've done here at the bottom. I'm going to do a few more examples so that you can get the hang of it and then give you a few to do by yourself. Okay, so I'm going to start here with sodium. Sodium has got 11 electrons, okay? So all you need to do in order to be able to do this is you need to know the order of the orbitals. So I need to know that it starts off with 1s, then it goes to 2s, then it goes to 2p, then it goes to 3s, and so on and so on and so on. With sodium, it's got 11 electrons. 2 of them will go into 1s2. Then you move on to the 2s orbital. You'll fill in another 2 electrons. That gives me 2 and 2 is 4. P can hold 6, so I can put 6 electrons into 2p, and I'm left with 1 electron to go into 3s. And that's your electron configuration for sodium. With phosphorus, I've got 15, so it's going to be 1s2, 2s2, 2p6. That's 10 electrons already assigned. After 2p6, I get 3s2. That's 12 electrons assigned. I've got another 3 to go. After 3s comes 3p. 3p can hold 6 in total. I've only got 3 left. There's my electron configuration for phosphorus. And again, when you're done, just have a quick add up. 2, 4, 10, 12, 15. Make sure you've drawn the right amounts. Calcium we've actually already done. We had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Again, once you do a couple of these and you get used to the order of the orbitals, it becomes straightforward. Let's have a look at cobalt, which is slightly harder. It's got 27 electrons, so beyond anything you would have done at GCSE. Starts off the same way. I've got 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so I've got 2, 4, 10, 12, 18 electrons. I've got another 9 electrons to go. Now, when I'm writing this, even though 4s is lower in energy, I do usually put the 3d first and then put the 4s next. It's just common convention to have all of the 3s together, although you are not incorrect if you put the 4s first. That is fine. Okay, I've got 9 electrons still to assign. The s is lower in energy, so the 2 electrons will go into my 4s orbital, leaving me with 7 electrons to go into d. Remember, you've got 5 d orbitals. Each can hold 2, which means your d subshell can hold 10 in total. So it's fine to put 7 there. Once you've done that, again, quick add up, make sure you've got it right. 2, 4, 10, 12, 18, and 7 is 25, and 2 is 27. The next one, I've just drawn out the shell just to speed things up slightly. Germanium, 32 electrons to assign. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and then I'm going to pause here for a second and have a look. So I've drawn 2, 4, 10, 12, 18 electrons. I've got another 14 electrons to go. Okay, so I'm going to go, remember, into 4s first. Okay, so there's 2 of my electrons into 4s. Then I go back and fill 3d. Remember, 3d can hold 10 electrons in total. So I can put 10 electrons into my 3d. That leaves me with 2, 4, 10, 12, 18, 28, 30. That leaves me with just 2 electrons left, which go into my 4p at the end. Vanadium, all right. 2, 2, 6, 2, 6. I'll do all that nice and quick. That's 18 electrons. I've got another 5 to go. I know I put my 2 into my 4s before going back to 3d. That leaves me with 3 electrons to go into 3d. Okay, so as long as you remember that 4s fills first, as long as you write the order, you know how many electrons each can hold in total, and you know that 4s fills before 3d, then this shouldn't be a problem, okay? Just a little bit of practice, this should be okay. One thing to note, though, is that there are 2 exceptions. One of those exceptions is chromium, okay? So chromium's got 24 electrons, so just 1 more than vanadium. So I'm going to fill it in initially, the same as I filled in vanadium. So 2, 2, 6, 2, and 6. When I get here, okay, I've already filled in 18 electrons. I've got 6 more to go. I know 4s fills first, so I'm thinking I'm going to put 2 in 4s and then 4 in 3d. In actual fact, instead of going 2 and 4, you go 1 and 5. And the reason is because this half-full d orbital, half-full d subshell is more stable than having a full s and 4 in a d. So it's just to do with stability. You have to learn it off by heart that it's an exception to the rule, that you end up with 1 and 5 instead of 2 and 4, as you may have been expecting. Have a go at doing nickel yourself, okay? You've got 28 electrons to go into nickel, so just press pause, fill in the electrons for nickel, and then press play again. Okay, so the first part should be okay. That's 18 electrons drawn. I've got 10 to go, 2 into 4s, 8 into 3d. That gives me my 28 electrons. After nickel, we've got copper, and copper is your other exception. So copper and chromium are your 2 exceptions. Okay, so chromium is one exception, copper is the other. So copper initially is going to be the same as what we've had before. Okay, but then you get here, you've drawn your 18 electrons, you've got 11 to go. You would be thinking 2 in the s, 9 in the d, but it's actually 1 in the s and 10 in the d. So it is still your 11 electrons, but instead of having a 2-9 split, you've got a 1-10 split. And again, that's to do with stability, having that full d subshell being more stable than only having 9 electrons in it. Okay, so just know that chromium and copper are your exceptions. But other than that, if you know your order of the orbitals, if you know how many electrons each of your subshells can hold, and if you know that the 4s is lower in energy and fills before 3d, then you shouldn't have any problems with these. They all are exactly the same. Just to double check, though, in an exam setting that you do have the right answer. Okay, so there's 2 checks that I would always do. The first is just to add your electrons and make sure it matches your atomic number. But the second is to make sure that your electron configuration fits the position on the periodic table. So on your periodic table, groups 1 and 2 are known as the S block elements. The transition elements across here are called the D block elements. And then over here on the far side, Groups 3, 4, 5, 6, 7, and 0, they are your p block elements. And what that means is that when you write the electron configuration of a p block element, the highest occupied orbital should be a p orbital. For a d block element, the highest occupied orbital should be a d, and for an s, the highest occupied orbital should be an s. So if we look here at sodium, okay, we can see sodium is in group 1. It is an s block element. And if we look at the electron configuration, the highest occupied orbital is indeed an s. Phosphorus is over here in group 5, so it's a p block. Highest occupied is a p. Calcium is an s block. Highest occupied is an s. Cobalt, germanium, vanadium, they're all D blocks, okay? Remember, D is higher in energy than 4S, so your highest occupied is 3D, vanadium 3D, chromium 3D, nickel 3D, and copper is also 3D. Sorry, I think I mentioned germanium there as a D block. It is in fact a P block. It's just over here, so it's in group 4, and you can see that germanium highest occupied is indeed a p orbital. The other thing you can do just in relation to periods, because sodium is in period 3, it should have 3 energy levels. So if we see here, sodium is in period 1, hydrogen's in period 1, lithium's period 2, sodium's period 3. So I've got 3 different energy levels, 1, 2, and 3. Phosphorus is also in period 3. If you come down here to your transition elements though, you've got period 1, 2, 3, 4. All of your transition elements there are in period 4. So you can see that your transition elements do have 4 energy levels represented, 1, 2, 3, and 4. So just once you've written your electron configuration, add up your electrons, make sure it matches the atomic number, and then compare it to the position on the periodic table. Make sure what you've written makes sense.